Today we're starting our very first lesson in the chapter over radicals. So the first lesson in chapter 11 is going to be about expressing roots. So begin by looking at the perfect squares from 1 to 20. So what that means is that when you do a perfect square, you're just multiplying a number by itself. So 1 squared would be 1. 2 squared would be 4. 3 squared would be 9. 4 squared would be 16. 5 squared would be 25, and so on all the way to 20 squared, which would be 400. So these right here, this list right here, is the list of perfect squares. So these are numbers that we got from taking a number and multiplying it by itself. So now we're going to list the perfect cubes of 1 to 10. So in a perfect square, we took a number and we multiplied it by itself. To get a perfect cubed, we're going to take a number and multiply it by itself and then multiply it by itself again. So 1 cubed would be 1 times 1 times 1. 2 cubed would be 2 times 2 times 2, which is 8. 3 cubed would be 3 times 3, which is 9, times 3 again, which would be 27. And then 4 cubed would be 64, 5 cubed would be 125, 6 cubed would be 216, 7 cubed would be 343, 8 cubed would be 512, 9 cubed would be 729, and then 10 cubed would be 10,000. So this is the list of perfect cubes. Now you might want to keep handy the list of perfect squares and the list of perfect cubes. It might help you do your assignment. So let's just begin on trying to remember what does it mean when you take the square root. So the square root of 16 is saying what number times what number is 16? Well, the answer with that would be 4. And then we have 361. So what number times what number is 361? Well, that would be 19. Now, this last problem is a little different because we've got 3 roots of 64. So we're saying what number times itself again is 64. Well, remember when we listed the perfect cubes, 64 was on the list of perfect cubes, and it was what you got when you did 4 times 4 times 4. So 3 roots of 64 would be 4. So squaring a number and taking the square root, those two operations are inverse operations. They undo each other. Just like addition and subtraction undo each other, multiplication and division undo each other, squaring a number and taking the square root of a number, those are inverse operations. So if we wanted to find the square roots of 9, we would have 3 and negative 3 because 3 squared is 9 and negative 3 squared is also 9. So a square root is one of a number's 2 equal factors. So a square root is just one number where it's a factor and the other factor is going to be equal to the first factor. So the factors are the same. So 3 and 3 or 4 and 4. So they're the same, they're equal. 3 is equal to 3. But when we say what's the square root of 9, we're just going to say 3. So the symbol for a square root is the radical sign. And then inside the radical sign, the expression that we have is actually called the radicand. So if they're saying the radicand, they're wanting the expression that's inside the radical sign. So the square root of 9 has 2 values. Either have positive 3 or negative 3 because positive 3 squared is 9 and negative 3 squared is also 9. But to avoid any confusion, we usually just use the radical sign to indicate the positive square root, and we call that the principal root. So principal root is going to be the positive root. If we want the negative square root, we will put a negative sign in front of the radical sign. So for example, if I want the square root of 9, I'm just going to list the principal root is 3. And if I wanted the negative root, then I would say, what's the negative square root of 9? And that would be negative 3. So let's look at an example. Square root of 4 is 2. The negative square root of 16 would be negative 4. So to indicate roots other than a square root, we're going to use what's called an index. And so the index goes right inside the radical sign, kind of like in the little nook that's created on the radical sign. A number inside that radical sign is called the index. So now if there is not a number there for the index, then we're just talking about a square root. But if there's an index there, then we're talking about a root other than a square root. So it looks just like here, and so see, notice that there's a little n, and that represents a root that's other than a square root. So that's where the index goes. So a cube root has the little 3 in the index, and it's one of a number's 3 equal factors. So a number times itself times itself. So again, it repeats 3 times, but it's equal. If you have an nth root, so you have an n index, it's one of a number's n equal factors. So if 2 to the third is 8, then 3 roots of 8 is 2, because 2 is repeated 3 times to get 8. So in example 2, we're going to do cubed root. So the cubed root of 125 is saying what number times itself again is 125. And that would, well, 5 cubed is 125. So that means that the cubed root of 125 has to be 5. So now let's do the 4 roots of 81. So you're thinking, what number to the 4th power is 81? Well, 3 to the 4th power is 81. So the 4th root of 81 would be 3. So an even root of a negative number does not exist in our real number system. So you cannot have a real number that's an even root of a negative number, because any number to an even power is going to be positive. So you can't have an even root of a negative number, because if you have an even power, then that negative is going to become positive. So it does not make sense. So you cannot have an even root of a negative number. However, you can have an odd root of a negative number, because a negative to an odd power is going to be negative. So you can have an odd root of a negative number. So let's look at an example. If I have the square root of -4, that's not a real number, because a square root is an even power. That's saying what number to the 2nd power is -4. Well, that doesn't exist, so it's not going to be a real number. However, if I'm saying what is the cubed root of -27 over 125, I'm saying what cubed is 27 over what cubed is 125. I'm going to make it negative, and a negative times a negative times a negative is going to be negative, so it does exist. So let's see, 3 cubed is 27, and 5 cubed is 125, which means that the cubed root of -27 over 125 is going to be -3/5. So let's do the 5th root of -32. So I'm thinking, what number to the 5th power is going to give me 32? Well, -2 to the 5th power is -32, because it's an odd power, which means that my radicand is going to be negative. So that makes sense. So -2 to the 5th power is going to be, and I take the 5th root of that, I end up with -2. So some radicals are rational numbers if they are perfect squares or perfect cubes, but there's a lot of radicals that are actually irrational numbers. So remember, irrational numbers are non-repeating, non-terminating decimals. So irrational numbers can either be stated exactly as radicals or approximated by rounding to a certain decimal place given by your instructions. So unless the directions say to round to a certain decimal place, you should not approximate. You should just leave it as a radical. Like, you don't want to take the square root of 7 if you know the square root of 7 is not a perfect square, so it's irrational. Well, then don't tell me what the long decimal of square root of 7 is. Just say the square root of 7, and that would be your answer. So, since 7 is between 4 and 9, then we would say the square root of 7 is between the square root of 4 and the square root of 9. So that means that the square root of 7 is between 2 and 3. And if we were to use a calculator and say, well, what's the square root of 7? We would get 2.645751311. So again, we wouldn't want to know the approximate answer. There's too many decimals there. So we would just leave it as the square root of 7, but we can approximate it by doing this. Step 1, think of the perfect squares that are before 7 and after 7. So if you're looking at your list of perfect squares, 4 comes before 7 and 9 comes after 7. Then we square root every number. So the square root of 4 is 2 and the square root of 9 is 3, which means the square root of 7 is between 2 and 3. If we were to round to the hundredths, the square root of 7 would be 2.65. So let's say we want to take this to approximate the square root of 129. So we find the two perfect squares that are before 129 and after 29. So we have 121 and 144. And if we were to square root each number, we would get that the square root of 129 is between 11 and 12. And if we were to approximate with the calculator, we would find that the square root of 129, if we round to the hundredths, is approximately 11.36, which makes sense because it should be between 11 and 12. So the square root of, now we're going to switch to doing cubed roots. So for cubed roots, you want to pull out that list of perfect cubes that we did at the beginning of this lesson, and we want to find the perfect cube before 50 and the perfect cube after 50. So that would have been 27 and 64. So now we're going to cube root each number. So the cube root of 27 is 3. Then we have the cube root of 50. And then the cube root of 64 is 4. Which means that the cube root of 50 has to be between 3 and 4. And if we were to evaluate that on a calculator, we would find that the cube root of 50, if we round to the hundredths place, would be approximately 3.684. So the definitions of roots and powers actually allow us to convert equations from exponential to radical form and then back and forth. We can go from radical to exponential as well. So in general, if we have b base to the nth power equals a number, then we can rewrite that as the nth root of that number, a, is equal to b, the base. So, and then because we are using variables for that definition, we are not only talking about integers anymore, we can actually talk about things that are not integers. We can convert between radical and exponential form by using this definition. X to the a over b is equivalent to the radical b roots of x to the a power. So notice the denominator of your exponent became the root, and the numerator of your exponent became the power of the radicand. So let's say we want to convert 5 to the 2/3. So remember, the denominator becomes your index, and then the numerator becomes your power. So now we have 3 roots of 5 squared. Well, 5 squared is 25. So now we have 3 roots of 25. Let's try another one. Let's convert 5 roots of x cubed. So remember, the index becomes the denominator of your fraction of your exponent. So instead of being x to the 3, we'll have x to the 3 over 5. All right, let's say that we want to convert 3 to the 1/2 times x to the 3/4 to a radical. So remember, the denominator becomes our index, but we've got 2 different denominators. So before we can do anything, we need to find the greatest common factor of 2 and 4 so we can get the least common denominator. So 3 to the 1/2, we're going to rewrite that as 3 to the 2/4. Now that we have a common denominator, that denominator is going to become our index. So now we have 4 roots of 3 squared x to the 3rd. So if we were to simplify 3 squared, that becomes 9. So now we have 4 roots of 9x cubed. All right, let's say we want to convert this radical into an exponential. So we have a root of 4. So remember, 4 becomes the denominator of all of our exponents. So first we look at the 7. The 7 doesn't look like it has an exponent, but it does. There's an invisible 1 right there, which means it becomes 7 to the 1/4. And then we have x to the 3, and so remember the 4 becomes the denominator, so we have 3 over 4. And then we have y to the 2nd, which when we convert it, the 4 becomes the denominator, so we have y to the 2 over 4. Well, 2 over 4 can be reduced to 1/2. So our final answer becomes 7 to the 1/4, x to the 3/4, and y to the 1/2. All right, go ahead and try some problems on your own.